So I'm not sure if there's a lady here. And so my topic today is large-scale user behavior analytics by Flink. So let's get to it. But first of all, let me introduce myself a little bit and the company I'm working in. So my name is Hao. I work in a leading cybersecurity company in China, which is called HanSight. Our headquarters is in Beijing, and our R&D center is in Chengdu, which I lived in. So I'm a member of the R&D center. So my main skills are, as you can see, data processing technologies. I use JVM-related languages such as Java, Scala, and Groovy and stuff. So I don't know if any of you has ever been to China or even Chengdu, the Panda City. So if you haven't, you really should go because it's really good and it's a lot of fun. And people even say it's the Amsterdam of China. Yeah, that's a little bit extravagant. So let's cut the chit chat and get to the point. So here's the agenda. I'm going to talk about 4 things, and I'm going to show you a demo at the end. First of all, I'm going to talk about what is user behavior analytics, what it does, and why we need streaming processing tools like Flink to work with the user behavior analytics system. And then on the secondly, I'm going to talk about some technical challenges we ran into when we try to build this real-time large-scale user behavior system. And the third part is CEP engine, which is not necessarily the Flink CEP. It's just a general idea. So CEP engine with Jules rules. What is Jules Rule? We'll get to that later. And finally, I'm going to talk about some new stuff in Flink 1.4 because that's a recent discovery. We had some recent attempt on using this native Flink CEP. So let's get to the first part. What is a user behavior analytics in cybersecurity? So in a nutshell, user behavior analytics system is trying to find the anomalies in behaviors. Basically, it has 2 categories, outsider attacks and insider attacks. For outsider attacks, it usually means a hacker trying to hack information from your company, and while an insider attack means employee, more specifically a leaving employee trying to steal information from your company. That's quite normal, actually. They can just email things to their personal email or just copy-paste things using flash drive. So that's kind of thing we are interested in. So how do we analyze it? How do we analyze all those behaviors, events? So here on the right, there's a diagram. You can see that we have all those different logs. You have server logs, network logs, database logs, application logs, security logs, Active Directory, or even application-defined, user-defined logs. So you put all those logs into this UBA system. It runs it with some algorithms and stuff, and then you get outputs. Outputs are basically divided into 3 parts. The first one is outsider attack, and the second one is insider attack, and as opposed to normal behaviors. So we want to find anomalies in normal behaviors. So what's the market look like right now? What's the trend? It used to be, so traditionally the UBA system used to be offline batch mode. We just ran historical logs, but recently people start adding some machine learning algorithms into it to make it more streamable, and make it like real. It's not just online. It's like a real, near real-time analysis. But it helps a lot, but not enough. We need some extra work to make the UBA system work. So what's the challenges? First of all, and the most important challenge is that for a typical UBA system, it's deployed in the large enterprise, which has like 10,000, more than 10,000 unique users, and you have to analyze their behaviors in more than 10 dimensions. And the second of all is detection of some attacks needs to be real-time. As you can see, real-time is a high demand right now. People don't just settle with the batch mode. So, and for the third one, detection logic, that's the business logic. So every company has their own requirements, has their own business logic. But essentially, it's a mixture of blacklists, rules, and machine learning algorithms. So you don't have just one solution to all the problems. You have different kind of scenarios. And the last one is the business logic needs to be customizable in near real time. And that means that you have to be able to change your rules on the fly. Not just like, not necessarily like a really real time, but it has to be near real time, like seconds delay is acceptable, but if it's minutes or even hours, it's not acceptable. So for the first one and the second one, it just fits into Flink world. It can be solved by Flink easily, but the third and the fourth one needs extra effort. So let's take a deep look. But first of all, let me talk about why we use Flink. First one is the foundation, streaming in nature. Flink is streaming in nature, that's what we need. And the second one is Flink supports all kinds of data sources such as CSV, Kafka, HBase, sockets, or even text files, all kinds of data sources. So, and the second one is Flink uses RocksDB as its data backend. So RocksDB is very fast. It's developed by Facebook. That's why Flink uses it, I guess. And the fourth one is high throughput. So we have tried many other like streaming tools like Spark and some other stuff, or maybe people use Storm, but actually Flink advanced all of them, so it can reach up to 10,000 EPS. And the last one is actually very important. It's the window capacity, window mechanism of Flink. So we have tumbling window, sliding window, or even the combination of those two. Oh, this one, highly customizable operator. So starting Flink 1.4, you have a full control of operators, not just like the previous version. You only have control of the job, so you can change the DAG. But with Flink 1.4, you can change the DAG to some extent. You don't change it. You don't actually change it, but you have some control of it. So let's get to the core part of our UBA system, and it's the architecture. So as you can see on the left, it's the source, it's the logs I just mentioned. So those are the inputs. You put this inputs in the core part, which is in the middle, and then it just runs some algorithms, some rule matching, and then it outputs the data, outputs the report, which is on the right side, the outside attack, inside attack, and normal behaviors. So those, the left and the right I just mentioned, so let's get to the middle part. And the middle part is the core of our system. So as you can see, Flink is here. Flink is at the bottom of the system, so it serves as a streaming engine. And the green part is the ETL part. ETL means like we have metric, we have entity relationship, we have a sequence. What are those things? I'll get to that later. So we translate these ETL elements into scenario rules. It's kind of translation. And then put those rules into the scenario rule engine. And with some help of machine learning, artificial intelligence algorithms, you can find those anomalies. So with all those part together, you got this results. It's a report here. So we have this nice user interface so that people can do some supervise on it, because maybe the system just made a mistake. It's not alert, it's not malicious. So you can mark it as malicious or not. And for this rule engine, as I mentioned, we have to support like dynamic rule update. So we have provided a rule engine configuration so users can change their rules dynamically on the fly. So here, for for the rule engine I'm going to talk about later is that we use Jules as the rule engine, which is a good tool. It's a very good tool, but it's a little bit complicated to use. You have to mind a lot of details here. So let's see what is Jules and why Jules. Rule engine is the most complicated component, especially like something like Jules. Jules is an Apache project. So Flink CEP, as we know, as you may have used it, it's easy to use and it's like generic, powerful, but and it's perfect for real-time streaming events analysis. But it has its own disadvantages because our scenario requires more dynamicity. But with Flink, you write this code, you cannot change it unless you change the rule and then recompile it and put it in the Flink. But with Jules rules, it can be hard deployed. How we do it, we'll get to it later. So that's why we first choose Jules. A little bit more about Jules here. So Jules is a business rule, as I mentioned. On the right side of the diagram, you can see it. Sorry. Here, it's an example of Jules rules. As you can see, it looks like Java, right? So you have this package import, and this whole closure is a definition of a rule. So you have this P is a variable of the instance of person, and whose name is Michael. So if you got this event whose name is Michael, you can do some actions. Here we changed his name from Michael to other, and then output this thing to the console. Or you can also declare an event. It's like declaring a class in Java. So, and with this event, you got the first instance of the event which doesn't have any conditions. That means every event matches the first condition. And for the second condition here is like another event which is after 5 seconds, but before 10 seconds of the first event. So that's the relationship between the two events. So when you got something that matched all those two conditions, you can do something here. Here what we do is to retract the first event. That means just clear it out of the memory. As it's like powerful, it has its pros and cons. Let's see what's the pros. It's a simple language for people who's familiar with Java. It's easy to use, and it's a seamless integration with Java. And most importantly, it can be dynamically configured. But it has its cons. We actually ran into a lot of like memory issues when using Jules. Jules is a very big project. It has its own aggregation functionalities. We tried to use it before, but it shows that its performance is not good. It's very slow, and it's like a resource consuming. So that's why we use Flink's tumbling window for the aggregation. So we put aggregations in the operators of Flink, not just use Jules. And if we like want to do event series like the last one, the example on the last page, you have 2 events and you want to know the relationship of the 2 events. That's the event series process. And it's resource consuming because Jules try to put every event in the memory in order to match something. So that's not desirable. So we do this lifecycle management in our application level. So I just talked about Jules. How do we write those Jules rules? How do we match those rules to our events, our behaviors? So here's the example. ETL needed by scenario rule engine. So we have 3 types of ETL, as I mentioned: metric, entity relationship, and sequence. So for metric, It basically means aggregations, like you want to calculate the sum, the average, or the min-max value of an event. And for entity relationship, you just want to know the connection between two events or two entities. For example, which user uses which device and what did it do. And for sequence, it's like you filter all those logs and then store the source by timestamp, and then you finally converted the states, and so everything is ordered. So all three ETLs are defining scenario rule engines. So as I mentioned, Jules engine is hard deployable, so all those things can be hard deployed to the system without any downtime. Those just definitions is confusing. Let's get to an example later. So how do we achieve this hard deployment? So with Flink, you have this nice coflag map function. So you can use it to process two streams. One is event stream, which is the data source stream, and the second is the rule stream, which is Jules engine streams. So how do we process it? ETL processors, we pass away related configurations from rules. That's kind of confusing. I don't know why I write this. I'll show you the ideas later with an example. And scenario rule engine parses the whole rule. What does it mean? Let's get to the example. So here again, typical Jules rule, we have three behaviors here. That's three conditions. For the first one, the condition is type equals metric / 1 hour. That means 1 hour tumbling window overfilled VPN logs. And this is the expression. Expression is VPN.type equals logon, and the result is failure. So that's for metric, the first element of ETL. And the second condition is an ER. ER is entity relationship. It means VPN user and the relationship between the VPN user and the device the user used. So we have a condition that anomaly score larger than 50. So those are conditions thrown into a machine learning algorithm, and you calculate the anomaly score. If it's over 50, you output this one. But here it also has a coincide with B1. That means like when the first condition is matched, and then your concern is on the second one. And for the third one is type equals sequence. The third element of the third type of ETL. Also, you have an anomaly score over than 50. That's coincide with B1 too. So all those three conditions are bound together to match a series of events. So you got all those matched events, and you collect B1, B2, B3 into your a collection, and you send this collection to Flink, and then you can sync those results to whatever store you want to sync. We have some, actually, that solution works well for short-term stuff because, as mentioned, Jules actually requires a lot of memory stuff. So but our company's clients usually have a long-term behavior requirement. By default, our algorithms analyze long-term behaviors, which is like over 3 months data, like financial data, and like anti-fraud data, something like that. So if we just put, so how do we tackle this problem, this large scale of data? We have, of course, 3 solutions. The first one is naive. It's by instinct. You put everything into Jules, but that's not going to work. It's not doable. It'll just run out of memory. And the second one is you provide an external DB, such as Redis or Memcache, something like that. It's key value store. You put intermediate data into this DB. And the third one is, of course, use Flink's built-in state mechanism. So you persist those operator state so that you can retrieve it later. Here's some problems. First of all, you need to maintain previous Windows state if you choose the third solution, because for a certain amount of time, for here it's like months. But the problem is Flink's built-in window mechanism just emits output and clears the window immediately after the window is passed. So that's not going to work. And also, the RuxDB store deletes all the records when window is purged. But that's changeable because you can just modify the source code, right? And results from Flink aggregation flooded into rules. So you have all those events calculated, and you want to put those results into rules to match a certain, to put it in the rules to match a certain rule. But this will just flood into rules, and you may run out of memory. Again, so I've been talking about memory a lot. That's the main issue we have been having. But there's a way to work around. Use external key value store like Redis. We tried that. Memcache, we also tried that. But none of them works because Flink is very fast. But all those stores are kind of slow. So it'll have back pressure for Flink. So that's not doable. You can just change the source code. So we try to add a time to leave property to RuxDB so that it doesn't delete the records. But it's not very to use because like different users have different requirements. But of course, you can just provide an interface for user to configure the time to leave. But again, it's you have to dive into the Flink's source code. You may run into some other problems you can't just imagine. So, and instead of just, besides making some optimization in Flink, we can also optimize the Jules. As I mentioned before, Jules memory management actually kind of sucks. So we can set up a threshold. So I just forgot, there's something I forgot to mention is that the facts. So what is a fact? Facts is a terminology in Jules. It's actually just an equivalent of events. So Jules, when event runs into Jules, Jules changes it to facts. So facts can be matched to a rules. So it can be matched facts or unmatched facts. So it stores all the facts in the memory. So that's the main reason you run into a memory issue. So what we do is to set up a threshold. When this number of facts reaches the threshold, we just clear everything and then restart this whole process. That's Flink with Jules. It works, but not very. The performance is not very desirable. So we recently found the plan B. Actually, it's a recent attempt of using Flink CEP version because previously we tried to use Flink CEP, but it just sometimes it just cannot meet our requirements because our clients may have some very complicated business logic. But this time, when starting Flink 1.4, we can use it because starting 1.4, you can solve the cannot hard deploy problem. So what we do is that we trigger a save point, and then we cancel this job, and then we change the rules, update it, and then deploy the rules into a Flink so we can resume this job. So for the first, this is the workflow. We'll get to that in the diagram later. So how do we achieve this hard deployment? So we can save the state of a unique identified operator. As I mentioned, that before 1.4, you only have control of jobs, so you don't have control of the fine-grained control of operators. But here you have. So you can save the state into a save point, and when you update your rules, you can just restore from the save point. Here are the rule issues by Flink. So hope Flink you guys can do something about it, because like our experience tells us like the 1.4 version is still a little bit basic. You can get around with it, but you may run into some other deep issues that we haven't found. So here's the workflow. You have a scenario rule, which is different than Jules. It's a language that we design. It's a Groovy-like language. I'm going to show you in the demo later. So you have these rules, people and the web interface, people write those rules, and then the whole system translate the rules into Groovy. That means you write a piece of expression, and you change the expression into runnable Groovy class, and then also Java class. And then you compile those generated Java and Groovy class into a jar, which is a rule jar. And then now you trigger the save point and cancel the previous job, and you deploy the new rule jar into Flink, and then you resume the job. So that's the whole process. The trick thing is here. So we design a language and also a parser to parse that language into Java code, and that means you can compile and run this Java code dynamically on the fly. So this is the tricky part. The performance is like this. We have three kind of jobs. Jobs with low number of events, jobs with medium number of events, and jobs with highly intensively large number of events. For the first two, for the first one, it works perfectly, and the second one, it works well. But for the last one, the system just slowed down significantly. But we have some solutions to fix that, which is here. Rules are, as I mentioned, that you only have one rule jar. If you have hundreds of rules, that'll be a problem, because every event will have to be matched by all the rules. The Flink CEP doesn't support that. It won't even start. It'll fail. It'll fail in the initialization phase. So the solution to fix that is that we can separate all those rules. So we can put some of the rules in a jar and some other rules in another jar. That means every jar doesn't have so that every jar doesn't have so many rules. And then you publish all those jars into Flink and start a multiple CEP stream. That'll fix this problem. So let's talk about how to optimize the DAG. As I mentioned, let's say you have like over 1,000 patterns. So like 100 patterns, and 100 rules, and each rule has a few patterns. So you have 1,000 patterns here. If you just map one pattern to one stream, that means when you start the Flink application, you have to initialize like thousands of streams, which will just run into out of memory instantly. You won't even be able to start it. So that's before Flink 1.4. You can only do this. But starting Flink 1.4, you have this you can map n patterns to one stream with this group pattern functionality. So here's the example. You have pattern 1, 2, 3, 4, 5, and you group this pattern into one pattern. And so for this pattern, you can stream a CEP stream for your matching stuff. But however, this is a new functionality, a nice one, but it doesn't have any optimizations, especially it doesn't have SQL optimizations. So for applications that relies on data events SQL stuff, it's just slow. Again, pros and cons. So simpler implementation. So because lots of things are done by the system, like writing Java code or compile. You don't have to worry about that. You just write your own rule according to our language. It's only 1/5 code of the Jules version, and it's better scalability and more parallelism. No more one big operator. With Jules, we have this one big operator that does all the aggregations, but this time it won't be like that. And it's easier to get runtime metrics because you have Flink, the UI. You can metric everything and of your concern. But it has its cons, as we said, that the whole system doesn't have downtime. It's running, but when you try to update the rule, your rule engine will have seconds of downtime. But I think that's reasonable and acceptable for our scenarios, because there may be some seconds you miss the attacks because your rule engine is off. But again, it's a streaming thing. You can just ignore those events. So what's the next step? So previously I talked about two solutions, Jules and native CAP stuff. So what we want to do is try to map Jules to Java translator. That is to map the first solution to the second solution. We are still working on it, and it looks like it's workable because Jules is just Java code. And the second one is optimization at event pattern level for better performance. That means we have to make some modifications on the Flink source code. So I've been talking about so much about the solutions we have. Here's a nice demo I want to show you so that you can have a better idea of what I was just talking about. It's a video demo because I just want to avoid the demo apocalypse. You never know. You never know, right? Every time you want to demo your program, it just failed. So this is a simple web interface. So you try to log in with admin and passwords. Now it doesn't have any alerts, so it gives you an error. So I have some preset rules here. Just one rule has two expressions. That is one rule with two patterns. The first pattern is the event's amount is larger than 19,000, and the second one is less than 300. So in order to make it run, we just click the publish button, and it will send this rule to Flink. So let's get back to alerts. Now you have some alerts here. So you can see all those amounts are either over 19,000 or less than 300. Yeah, you can check that. Let's get back to the rules. Now we change it to 500 and publish it. And try to refresh the results. Maybe you can't see it. Can you see it? The projection is a little bit off. Okay, here. There's a 200 stuff. Maybe you cannot see it. 300 stuff, sorry. That's over 300. That means our new rule just took effect. So this time, try to disable it. That means we have no rule in the system at all. That means everything is fine. Everything can go through. So there won't be any alerts anymore. No new alerts. Let's get back to the rule. Add a new rule. This time, it won't be that easy. We want to add an aggregation rule, which uses the sliding window stuff. So we have a aggregation in 5 seconds. That's 5-second sliding window, and in the 10-second tumbling window. Oh, okay. So here are the new alerts. Okay, so you can see here we have all those aggregation results. For example, we have the mean, the max, and the count, the sum. Apparently, the sum is over 100,000. Our rule is trying to find the sum which is larger than 100,000. Okay, there's only one rule that's active right now. Let's bring back the first rule. Let's see the result. Okay, this is a new result. That means both of the rules are taking effect. Okay, that's it from the demo. So that's my topic today. Any questions? Anyone? Yes, please.
Just probably. I'm not sure if it works. I think not. No. Yeah. So I just wanted to ask, first of all, about parallelism, because I didn't get exactly where Flink is and where Jules is. So in the beginning, before ingesting the data into Jules, you use Flink.
Yep.
So in this case, I would like to ask, first of all, how do you achieve parallelism if your stream is keyed, essentially?
Mm-hmm.
And the second question is, how do you handle event time and out-of-order events? Or you rely totally on Flink before arriving to Jules to handle the event time order?
Okay, so the idea is that the Flink and Jules are different modules. They are not that coupled together. So what you do with Flink is what you do with any other simple Flink applications. You work on the timestamp, you work on the watermark yourself, and you do some aggregations in the Flink operators. And then that's the result. You send this result to another operator, which is a Jules operator. So you send this result to Jules, and Jules will match its rules. And then if it matches, as I showed you before in the slides, that we have a rule with 3 conditions. So those input are actually Flink's first aggregation operator's output. So we send those into Jules, and then it matches. If it matches, then you send it back to Flink, and Flink can just sync it to your data store.
Yeah, thanks.
Okay, so I have a question about your rules usage. Do I understand correctly that you have stateful sessions for each of the keys?
Yes.
And the session will kind of last forever, right? Potentially. And that's why you have to clear it up?
Yes,
okay.
Because our scenario is like our clients are most from the financial world, so their data has to be stored for months. So we save all those data into RocksDB instead of memory, because you can't do that. No memory can contain such data, right? So we take advantage of the RocksDB stuff and save point.
And the second question is, do you currently use Jules Fusion, the time-based Jules model?
Time-based Jules model?
Yeah.
We tried that. It's not working. Just like the
so it's still not working
the
for large amounts of data.
Yes, just like the aggregation from Jules. So you can only do simple match. that's why we calculate all the aggregation value and then send it to Jules. If you use like the serial functionality of Jules, it's still going to run into memory stuff issues.
Thanks.
I have two questions. One is maybe just a clarification. I may have missed the first minutes of the talk. So do you actually run the Jules code inside the Flink function, or are these two different processes?
Jules function are one of the operators in Flink.
Okay, good, cool. The other question is maybe this is a bit more of a thought actually. So you described this interesting model at the beginning where you said here's the co-flat map or co-process function, and you take the event stream and the configuration stream.
Yeah.
Have you ever tried doing something like taking the, let's say, the Flink CP operator code, or something similar? It could be like just Java code compiled from your rules, and running this inside like a co-flat map or a co-process, and then applying the same trick in the sense of whenever you want to reconfigure the CEP pattern, you actually push some encoding of that pattern to the stream, or you might even just push the compiled bytecode of that pattern actually through the configuration stream, and then just instantiate it in the operator and run it like that. Have you ever tried something like that? Or?
Actually, what you just talked about is the next step I just talked about in the demo here. Let me show you. So here, we're just talking about how if we can just mix the Jules rules and the CEP pattern. So that, because I just talked about two solutions. One is Jules. It's just basic workflow. You get results from Flink and you send this data to Jules and you match it. And the second one is just take advantage of 1.4 CEP, Flink CEP, which you can generate the pattern code and compile it and just publish it to Flink. So what we want to do next is to mix all these two stuff so that we can have a Jules rule, so that we don't have to define our language. We just use Jules, and then we compile it and put it in the operator and run it. Yeah.
I think once that is done, if you have any interest in making that open source, I think a lot of folks would be interested in something like that. That sounds like a really cool solution.
Yeah, I hope so. Yeah. Anyone else? No one? Okay, I guess that's it. Thank you for listening.